Okay, so this is a video about chapter 4. From this chapter, we're going to talk about everything about regressions. So chapter 4 is going to start with the most simple regression, which is called the linear regression with one regressor. Okay, so basically we're going to introduce population regression and sample regression. We're going to introduce the estimator. We're going to talk about the measure of fit. And then we'll also talk about assumptions for causal inference. Remember that we will use the estimator to estimate a population parameter, and we want to use it for causal inference and for prediction. Okay. So what is linear regression? It's a regression line in short, okay? We have a slope and have an intercept. It can be used for causal inference or prediction. Okay, they place different requirements on the data, and there will be different things that we need to be careful about. So we'll talk more further into it. Okay. The problem of statistical inference for linear regression is actually the same for estimating a mean. Okay. Remember what's the challenge of estimating a mean? That we know that the mean that we get is a sample mean. And we want to use the sample mean to talk about something about the population mean, which we will never know, right? And there will be accuracy about how much the sample mean is close to the population mean. And and in order to do that, we will use central limit theorem. We try to get a distribution of the sample mean. So here it is actually the same. So when we draw a line, when we try to estimate a slope, we know that the slope we get is a sample slope. Okay. We want to use the sample slope to tell something about the population slope, which we will never know. So we need to know how accurate it's a sample slope. So sample slope, is it unbiased? Is it consistent? What's its distribution look like as an estimator? And how do I use that estimator distribution to have something to say about, okay, this is the sample slope I get, and I believe that the confidence interval is how much from what to what, and I believe that I can use that to test a hypothesis, and I can reject or fail to reject a hypothesis. Okay, so in a general picture, in a big picture, the estimation process is the same. Okay. All right, so let's get into the regression model, and then we'll have a better idea about what it is. So for example, we want to run a regression line between test scores and student-teacher ratio. Here we call it STR. Okay. So beta 1 here is the slope of population regression line. Okay. Why are beta 0 and beta 1 population parameters? So every time when we say population parameters, it is the one in the real world, or we call that the truth that we will never know. Okay. So we would like to know about it, but we will never know. Okay. But we must estimate it using the data we have. Okay. All right. So here, this is still the population slope. Okay. There's y equals to beta 0 plus beta 1 times x. What is u? Okay. U is called the regression error. Sometimes you can also call it population error. Okay. Sometimes it's also called just error. Okay. or you can call it population error, but not very often. Okay, it's also called error. Okay, let me write it down. Population error is also right. Okay. Um, so the regression error, what does it mean? Um, it means that uh, it's all the omitted factors. Um, so omitted factors is all the other factors that can influence y, other than the variable x. Okay. So what does this regression equation actually means? It means that y is, let's say, y we call it dependent variable. So y can be test scores. Test scores is a function of the independent variable, or we can call it regressor. Okay, so it's a linear function of the independent variables that we can measure. But y can also be explained by u, which is all the other factors except x. Okay. So here, this line means that y can be explained by x and u. Okay. You can think of u is everything except s. Everything that determines y except x. Okay. So we'll have an example about u later. Okay. All right. So all of these names are very important to remember. Okay. Especially understanding the u is important because we will talk about some assumptions we have for u later. Okay. All right. So we also have a lowercase n. Remember what lowercase n is? Lowercase n here is sample size. Okay, so I equals to 1 to n means that you have I observations, and each observations you observe their y and you observe their x. Okay. All right. So this is an example. Okay. Um, Again, test score is the y. Oh, it already writes down. Okay, so test score is the y. Student teacher ratio is the x, STR. You have 1, 2, 3, 4, 5, 6, 7. You have 7 observations. Okay, so it's 7 dots. And now you want to draw a line. Okay, this line has 2 parameters. The first parameter is beta 0. Okay, beta 0 is here. The second one is the slope. Okay, this is the slope. So the slope is negative. Okay, the slope is negative because it's downward. Okay, it means that if you increase x, y is gonna decrease. Okay, that makes sense because if you put more students into the class, then the student grades is gonna decrease because we believe that maybe the teacher cannot have that much attention on each student. Okay, so there are dots around this line, but not exactly on the line. Why? Because there will be other things that determines test scores. Okay, think about what the other things can be. It could be the average income level of the students. Okay, it can be the average schooling funding of the per capita of the school. Okay, it could also be how good are the students in different districts. Okay, for example, some districts are let's say, a lot of immigrant families. Okay. And these immigrant families, if they don't speak very well English, well, of course, some immigrant families speak very good English. But if you are in some, let's say, communities that students don't have a very good um, language abilities, then it's not just the student-teacher ratio that explains why. All the other factors and also explains why. So the difference uh, between the line to the dot, or to the dot, from the dot to the line. Okay, this is a vertical this difference. So the difference between it is the u. Okay, so you can think of u as everything else that makes the dot not exactly on the line. Okay. All right. So u is all the other things that explains why, explains, in this case, explains test scores, but cannot be observed, okay? Because we don't have data for any other things. The only thing we know is student-teacher ratio and test scores, okay? If I can measure income, then I can put income in, but now I don't have it. So U is all the other things, okay? Now we have draw the line. So how do we draw this line is the question, okay? Next. So this is how we estimate beta 0 and beta 1 from the data. We want to estimate the least square estimator, okay? And least square estimator basically solves this problem, okay? This is the least square estimator of y bar, okay? Some of you might not be familiar with what this is. So this is saying that I want to minimize the summation of all these things, okay? And I will end up getting an M that minimize the whole thing of what I circled in this red rectangle, okay? And this M is the y bar, okay? This M is the y bar, which is a sample mean. Okay, by analogy, we'll focus on the least square estimator or OLS estimator of the unknown parameters of of beta 0 and beta 1. Okay, so now we're gonna solve this thing by finding the optimal beta 0 and beta 1. Okay, and finding the beta 0 and beta 1 that minimize this whole thing will be our estimator, which is beta 0 hat and beta 1 hat. Okay, so you can think of beta 0 hat and beta 1 hat are similar to the idea about y bar. Okay, how about mu? Mu is the population mean. And in this case, beta 0 and beta 1 are the population parameter. Okay, probably use another color. Okay, so these are population parameters, while these are sample estimator. Okay, we have population parameters that we want to know, but we never know. And we have sample estimator, which is the variable for us to calculate the sample estimate. And this estimate can help us tell something about the population parameter. Okay. Okay, these are sample. Okay. And these are population. Okay. All right. So let's take a look at how they calculate that. Okay. All right. So in reality, you have way more than 7 dots, and you want to calculate the slope. Okay, you want to draw a line, but you don't know how to draw it. And the answer is to minimize the distance between this every point. Okay, so you can think of, you have all the points, and then there is a distance, there's a vertical distance between every point to the line, right? And you want to minimize the summation of all of these vertical lines. Okay. Okay, you minimize the sum of all the vertical lines. Okay. But these vertical lines have to take a square, because some of the vertical lines is positive, some of the vertical lines is negative. Okay, because what you do is y minus, it looks like this. Okay, so because you're getting, okay, come back here. So because you are getting y minus b0 plus b1x, so this is the point at the line, and this is the point of the data. Okay, this beta 1 plus beta 1, sorry, this beta 0 plus beta 1x is the point on the line, and yi is the point, it's a real point, a real data point. Okay, so come back here. So you're getting y, which is the point, minus the point on the line. So let's say this line is positive, but this line will be negative. That's why we need to take a square to make it positive. Okay, take square to make to make the u, to make them positive. Okay, just I don't have a name for them, but we have to make them positive. Okay, all right, so this is a mathematical process. I'll go through it for all of you, because some of you might want to pursue a very quantitative career that requires you to have an idea about how you can get it mathematically, but it is not required. Okay. Okay, so next. All right. No, these are the results. Where is the mathematical process? Uh-oh, it's not here. Okay. Okay, so basically it looks like this. You have to, let's say this thing, you call that, you give it a name that is A, okay? So then you take a derivative of A to beta 1, okay? And you get a bunch of derivatives, okay? This is what you're gonna get. Okay, this is 2 summation of 2 times y minus beta 0. B0 or beta 0 is the same. X. Okay. And then times x and times minus 1. Okay, it looks like this. and then you have a summation from I to n. Okay, because you're minimizing this whole thing, so the derivatives should equal to 0. Okay, there is an I here. All right. Okay, and solving this thing will get you beta 1 hat. Okay, why do we change that to beta 1 hat? Because it is how to say, it is called the how to say, this is called the estimator. Okay, so beta 0 is gonna disappear, so beta 1 hat will eventually equal to xi minus x bar, yi minus y bar. The explanation of x bar and y bar is the same with the sample mean. Okay. And then there is a summation here that goes with xi minus x square. Okay, I encourage you to go through this process, but it is not required. Okay, and then at the end, this part can be interpreted as kind of like the covariance of x and y. Okay, but it is a sample covariance, so it is s lowercase s xy. Okay, over here you can think of it as the sample variance of x. Okay, so it is lowercase s square x. Okay, so this is how you get beta 1 hat. Okay, and then I'm gonna show you how to get beta 0 hat. Whoops. Probably add one more. Okay. Beta 0 hat. How do we get beta 0 hat? So beta 0 hat, how do we get it? We don't get it by taking derivatives. Okay, so not from derivative. We don't need to take this, but because we know that beta 0 hat is the intercept, so x bar, y bar go through this line. Okay, so beta 0 hat equals to y bar minus beta 1 hat. Okay, beta 1 hat is solved from taking derivatives, equals to 0 times x bar. Okay, so step 1, step 2. Okay, again, I want to say that this process is not required, but I hope you guys have an idea about how the beta 1 hat and beta 0 hat comes from, so that in the future, if you come across a lot of technical issues and you are pursuing a very quantitative career, then these things will be useful. Okay. All right. I don't want to get you too upset with these things if you are not that into it. Okay, so beta 1 hat equals to the covariance of x and y divided by the sample variance of x. Beta 0 equals to y bar minus beta 1 hat times x bar. Okay, a very important thing is that x bar, y bar, this point goes through the sample regression line. Okay, which one is the sample regression line? This one. Okay, this is what we call the sample regression line. Okay, so sample regression line uses y hat equals to beta 0 hat plus beta 1 hat times x. Okay, be careful. We have y hat here, but we don't have x hat here. So x are the still x, the same x, but y becomes y hat. Why? Because y hat are the OS predicted values. Okay, so x, y hat are the points on the line. Okay, and then lastly, we have u hat. Okay, everyone's getting confused, but I need you guys to understand all of these and remember their names. U hat is the distance between yi and y hat. Okay, y hat is the vertical point on the line. Okay, so let's take a look at an example. Okay. Okay, let's take a look at this one. All right, so we have a bunch of school districts, and we observe their STR and test scores, and we run a regression, and we get a sample regression line that equals to test score, that is test score hat equals to 698.9 minus 2.28 times STR. Okay, so this is y hat. This is beta 0 hat. And this is beta 1 hat. Okay, but STR is the same. So where is y hat? For example, if you look at this dot, here is y hat. Okay, here is x, y hat. Okay. What is the u hat? So u hat will be the difference between 2 points. Okay. If the point is above the line, then u hat is positive. If the point is below the line, then u hat is negative. Okay. All right. So we usually care beta 1 hat a lot because it tells us the relation between x and y. So here it says that if you increase student-teacher ratio by 1 unit, then test score is gonna drop 2.28 unit. Okay. Is that a big number? We don't know. We have to interpret that in a broad sense, okay, in the reality sense. But this is how we interpret the beta 1 hat. Okay. All right. Okay, this is more about the slope. So districts with one more student per teacher on average have test scores that are 2.28 points lower. And you can use delta to represent the change of each variable. So for example, this one, change of the STR and change of test score conditional on STR is minus 2.28. Okay. I want to point out that this thing can also directly written as the change of test score over the change of STR. Okay, and this will also make sense. Okay. All right. The intercept, take literally, means that according to this estimated line, districts with 0 students, okay, districts with 0 students per teacher would have a test score of 698.9. But is this realistic? Okay, 0 student per teacher. This is not realistic, okay? It makes no sense. So in this specific case, beta 0 doesn't have a meaning. But in some cases, if x equals to 0 has a real world sense, then beta 0 will have an economic meaning. Okay. All right. That is why we always care about beta 1 more than beta 0. Okay. Okay. So now you can also make prediction. For example, one of the district is called antelope. For which STR is 19.33, can you predict its test scores? Okay. Suppose you don't know the test score, then you predict that antelope test score is 698.9 minus 2.28 times 90.33. Okay. This is what your prediction looks like, which is 654. However, its actual test score is actually above that. Okay, so there will be some other things in the error term that is contributing to its overperformance. Okay, so residual, okay, pay attention to this name, it's not called error. Residual equals to 657.8 minus its prediction. Okay, so suppose this one is antelope. Okay, then residual is 657.8 minus its prediction, which is on the line, which is 654. Okay. All right. This is the Stata output. Okay. We will not learn Stata output in this semester. Okay. In the later part, I will teach you guys how to run a regression on Excel and also on Python. All right. So I probably want to emphasize one more thing. Okay, so how do I introduce a table? Okay, good. Remember we have population, and everything corresponding to it is called sample. In population, we have population line. So population line is y equals to beta 0 plus beta 1 times x plus u. Okay, while sample line is y hat, okay, equals to beta 0 hat. Okay, because now you have sample, you use an estimator, plus beta 1 hat times x. Okay. You have population parameter, let's say intercept. Okay, so it is beta 0. Okay. For my convenience, I just write beta 0, but it's the same with this one. Okay. For sample, you also have sample intercept. Okay. It is called beta 0 hat. Okay. What else? You have population slope, which is beta 1. And you have sample slope, which is beta 1 hat. All right. The last thing is population error. And in sample, you call that residual. Okay, so this is the only thing that has a different name. Whoops. So I wanna point it out. Okay, so in population error is U, but in sample, residual is called U hat. Okay, or you can write it down as U hat. Okay, what does U hat equals to? U hat equals to Y hat. Wait, no. It's Y minus Y hat. Okay. So what is Y hat? Prediction. we don't call it sample prediction, we just call it prediction or predictive value or predictive value. Okay, so predictive value is y hat. Okay, all right. Predictive value is the same with the one that is called the line, because predictive value is on the line. Okay, it's very easy to understand. All right, but we don't put x and y here, simply because x and y are observed, or sometimes not observed. Okay. Yep. These are the things. These are the names that you from so far you need to understand. Probably put it here as well. This is called sample line or sample regression line. Okay. And then you have sample intercept. You have sample slope. Oops. And here, all of these should be called population. Oops. How do I? Population regression line. Okay, this is better. And population intercept, population slope. We don't call it population error, but if you say population error, I still know what you mean. Okay. We don't call it sample residual, but just residual is okay. And we don't call it sample prediction. We simply just call it prediction or predictive value. Okay, and predictive value will be y hat. Okay, will be a point on the line. All right. Okay, so these all of these names should be very, very clear. Okay. So here, notice that there is, okay, one more difference, slight difference. There's a U in population regression line, but there isn't a U hat here. So this is sometimes controversial. So this one can be here or doesn't really need to be here. There isn't a really consensus about this. I think that if it's a line, then it shouldn't include a U. But some textbooks also include a U, just saying that, oh, in the population line, you need to know that U is part of the population error instead of a sample residual. Okay, so it's a little bit confusing, but it's okay. Okay, it's manageable. All right, so this part we are done. Next, we're going to talk about measures of fit. Okay, so how well does this line fit all of our data points? So here we introduce something called Regression R Square. It measures the fraction of the variance that is explained by X. Okay, it is unitless. Okay, unitless. Okay, this thing can appear in your multiple choice question, and it ranges between 0 and 1. Okay, this can also appear in your multiple choice question. We also have another thing that can measure the fit, which is called SER, standard error of the regression. Standard error of the regression has unit. Okay, it has the same unit of y. Okay, so for example, if y is kilometers, then SER's unit is kilometers. If y is test score, it's 1 score, 2 score, then the unit of SER is also score. Okay, so if it's score, then SER can be larger than 1. Okay. R square is commonly used, but SER not that much. So you need to understand R square first. Okay. Now, next, how do we define R square? Okay. R square is the part that is explained divided by the total variation of y. Okay. So TSS is total, I don't remember the name. It's total variation of y. And ESS is the explained variation of y. So okay, this is the part that is explained, and then the total variation is just the variation that you know. Okay. All right. So if R square equals to 0, that means that your line doesn't explain any variation. So this one means that uh, your line is horizontal. Okay, it means your beta 0 is, sorry, your beta 1 is 0. Oops. It means that your beta 1 hat is 0, that your line is horizontal. Okay, it doesn't have any variation vertically. R1 means that ESS equals to TSS. Okay, what does that mean? That means you have a line and all of your data points are on the line. Okay, that means that your line completely fit all of your data. Okay, so, and this, all of your points are not on the data. Okay. Um, R square is between 0 and 1. Okay, it's always between 0 and 1. It doesn't have a unit. For R square, for regression with a single R, of single X, R square is the square of the correlation coefficient between X and Y. This thing is optional. You don't need to remember it. Okay, you just need to know that R square, what does R square equals to 0 mean? What does R square equals to 1 mean? R square is unitless. It's between 0 and 1. And understanding what this part mean. Okay, the last part is optional. Okay. SCR, I'll go through it quickly because it's not commonly used. So it is the sample standard deviation of the residual. Okay, because there is a degree of freedom loss, so your n will -2. Okay, you end up having SCR's equation like this, but this equation is not required. Okay, it's only optional. All right. So for SER, what you need to know is just it measures the spread of how spread out is your U. And you need to know that its unit is the same with Y. All right. And then the last thing is the root mean square error. Okay. It is also closely related to SCR. It looks like this. So what's the difference between this one and SCR? SCR is divided by n minus 2, but this one is just divided by n. Okay. It is not required. Okay. This thing will not appear in any of your exercise because it's just not commonly used. Okay. All right. Oops. All right. Okay. So let's see an example of R square and SER. For example, this regression R square equals to 0.05. So it means that the variation of all the test scores can be 5% of the variation of test score can be explained by student-teacher ratio. Okay, and 95% of the variation can be explained by the student's IQ, the teacher's ability, or the student's family income, or the student district's funding resources and all those things. So all the other things explain 95% of the variation, while STR explains 5%. Okay. Is 5% high? Maybe not. But is this effect enough for us to convince the government to spend more money on hiring more teacher? This will be a political question to answer. So the economists only answer the first part. That is, if it matters, what's the scale and how much of the variance is explained by it. Okay. All right, and STR equals to 18.6. That is saying that 18.6, that is saying that the spread out of the residual is 18.6 test scores. Okay. STR explain only a small fraction of the variation in test scores. Does this make sense? I think so, because if only hiring teacher can make you feel, make you score higher test scores, then why don't you just hire one teacher for every student, right? It doesn't work that way. So there are a lot of other things that can explain the test scores. Students' motivation, their own ability, or their own dedication to study hard. All of those things matters, not just the amount of teachers that we hire. So in this case, we believe that this number 5% or 0.05 makes sense. Okay, so that's the part of measures of fit. All right, so here comes the least square assumptions for causal inference. So far we have treated OLS as a way to draw a straight line through the data on X and Y. Under what conditions does the slope of this line have a causal interpretation? That is, when will the OLS estimator be unbiased for the causal effect of X on Y? Okay. And what is the variance of the OLS estimator over repeated samples? Okay. So repeated samples, think about Y bar of repeated samples. How would that data distributed? So to answer these questions, we need to make some assumptions. If you want to find something that is comparable, think about central limit theorem. So in central limit theorem, we assume that n is large. We assume that we have random sampling. So for running a regression, we also have some, actually 3 assumptions that is known as the least square assumptions for causal inference. Okay. All right, so let's get into it. I already explained causal effect about a lot to you. That is, how do we know that the test scores are caused by student-teacher ratio, not by something else? Okay, and in this case, let's jump to the assumptions first. Okay, so there are several things that are important for the assumptions. So first, conditional distribution of U given X has mean 0. Okay, all right. So this equation, you have to understand what it means. It means that expectation of U conditional on variable X equals to any value lowercase x equal to 0. Okay, even if this one is hard to understand, its implication has to be remembered. Okay, this implies that beta 1 is unbiased for the causal effect beta 1. Okay, beta 1 is our estimator. Causal effect beta 1 is the population parameter or population effect that we will never know, but we want to know if it's out there. Okay. We still need IID. Okay, remember IID is independent and identically distributed. It simply means random sampling. Okay, and the last assumptions is that large outliers in X and Y are rare. Technically, they say that X and Y have finite fourth moment. Okay, but this one is easy to understand. We don't want large outliers to draw our results away. Okay, so I can give you an example. Um, for example, this is our regression line. It is student-teacher ratio on test scores, and your data look like this. Okay. All right. So this looks good, but if you have an outlier that's over here, you have some outlier that's over here, which doesn't make sense, or it's due to data error, then you can probably get a wrong line that looks like this. Okay, so you don't want to have that. So the third assumptions is also important. Okay. All right. So let's take a look into each assumptions one by one. The first one, it looks complicated. It looks complicated. It's kind of like, oh, at each point you have a distribution of U. Okay. You have a distribution of U. You can think of the U looks like this. So this is 0 for U, and this is the normal distribution of U. Okay. If your axis is here, then it's distribution of Y. Okay, doesn't matter. I wouldn't force you to understand this in a very mathematical way, but the best way to remember this is just X and U is not correlated. Correlated. Okay. So here comes the question, what is U? Remember what I say at the beginning. So U is everything else that explains Y. Okay. So how do we have X and U, or X and everything else that are not related? Then you have to argue that, okay, I think everything else include family income, and or include students' IQ, or include students' dedication to work. Okay, then you have to argue that I believe that student-teacher ratio is not related to any of those things. Okay, let's say student-teacher ratio is not related to whether a student work hard or not. Okay, you can have students who work very hard in a large class, or you can have students who work very lazy in a small class, or the reverse. So all the other factors is not related to X, okay, or not correlated with X. They don't increase or decrease with X increasing. So if that assumption holds, then this first assumption is valid, okay? That means expectation of U conditional on X is 0, okay? So here is the slides explanation. Okay, the benchmark of understanding this assumption is to consider an idealized randomly controlled experiment. I believe I've talked about this before. So if X is randomly assigned to people, so you randomly assign students into different class sizes, so then all the other things will not be related to X anymore, right? All the other things like family characteristic, student characteristic, or geographic characteristic will not be related to X anymore. Then all the other things, which is U, is independent of x, okay, then this assumption holds. Okay. It's a little bit difficult to understand, but I believe that when we talk about the omitted variable bias, you guys will have a better understanding of it. Okay. And let's quickly go through assumption 2. Okay, this one is simple. Okay. Random IID means random sampling. You have to have random sampling in central limit theorem, right? To get y bar, you have to have random sample. And here, to get beta 0 hat and beta 1 hat, you also need random sample. Okay. And this is the fourth moment. Okay. So fourth moment is finite, which means that you don't have a lot of extreme values. Okay. This one is also easy to understand. It will only appear in some multiple choice questions. Okay. Even assumption 1 will only appear in multiple choice question. Okay, there isn't any equation here for you to calculate yet. Okay, all right. This is another example that OLS can be sensitive to an outlier. Okay, if there's an outlier, then your regression line can be biased. Okay. All right. Section 4.5. The OLS estimator is computed from a sample of data, and we want to get the sampling distribution of beta 1 hat. Okay. We want beta 0 hat's distribution as well, but once we know beta 1 hat, then it's easy to know beta 0 hat. Okay. And in most of the situation, we only care about beta 1 hat because beta 1 hat always has a meaning, but beta 0 has not always. Okay, so this is a framework. You have a population that you're interested in. You have random variables, that's x and y. This is something you can measure. You have 3 assumptions, okay? The first assumption that it is linear. The second one is u and x are independent, okay? The third one is it has finite moment. And okay, this is the third assumption. The fourth assumption. No, I don't think. These 3 are the least square assumptions, but the first one, we just naturally assume that it's true, okay? All right, so using this framework, we'll try to get to the sampling distribution of beta 1 hat, okay? It is similar to y bar, which has a sampled length distribution, okay? I'll probably go through this part because there are too many equations here. Okay, so this part, it's only for you to try to get to understand how we calculate the distribution of beta 1 hat and beta 1 hat, which includes its variance and also standard error and mean. Okay. So page 34 to page 39 is optional because this process is not really required. So what are these pages trying to do? It is trying to get to oh, I think I added one more page. Anyways, so these several page of equations are trying to get the mean and standard error of beta 1 hat. Okay. Let me think if we need to get to. Okay. Okay, how about I just make a comparison between this and central limit theorem. Let me add a page, okay, so that you guys would not be freaked out because of all of these equations. All right. Remember, okay. First, central limit theorem. Okay, central limit theorem has some assumptions, right? First, n is large. Second, you need IID. Okay, and then once you have all of these, then y bar is unbiased. No. Y bar is normal, and its mean is exactly mu y. Okay, so if its mean is exactly mu y, then it means that it is unbiased. And its variation, we call that standard error. Okay, and this standard error, how much is the standard error? It is sigma squared divided by n, and then you take a square root, or s squared divided by n, and then take a square root. Okay, you can also write it as sigma divided by square root of n, or lowercase s divided by lowercase s divided by square root of n. Okay, so this is central limit theorem. Okay. And then in an OLS, in a regression, there isn't a name for a theorem. So no name theorem. Okay, so there is a name here, but you need some of the assumptions that I mentioned. The first one is IID. The second one is expectation of u conditional on x equals to 0, which simply means that x and u should not be correlated. Okay, they should be independent. The third one is no outliers, or no a lot of outliers. Okay. Nope. Okay. So 3 assumptions, and then now you know that using these 3 assumptions with the equations from page 34 to page 39, you can get beta 1 hat, which is normal. All right. That its mean is exactly beta 1. Okay. What does that mean? It means that if this one means that y bar is, okay, let's say this one means that y bar is unbiased, then this thing means this beta 1, this mean equals to beta 1 means that beta 1 hat is also unbiased. Okay. All right. We need its standard error because we want to calculate t statistic and confidence interval, right? So how much is its standard error? Its standard error is very confusing. So let's forget about it. Okay. Even if you go to a PhD, you don't calculate it by yourself. Okay. But if you really want to calculate it, it looks like this. Maybe you want to calculate it. How do I know? All right, it looks like this. Okay. All right, you don't need to calculate that. Okay, forget about it. Um, but you need to know that both of these standard errors is decreasing with n. Okay, the larger the sample size, the more narrow your estimator gets. Okay. Um, okay, don't freak out because of this. There's no need to. Okay. Mm, Oops. Mm, uh, okay. You can take some notes here. Okay. All right, so central limit theorem and the theorem below, which I didn't which there isn't a name for it, and I can't give it a name, but basically says that once you have all of these assumptions, and then you can have an unbiased estimator, and you can also know the distribution of the estimator, so that once you have its mean, once you have its standard error, you can do all the other things that we do, which is calculating t-statistics and testing a hypothesis or calculating confidence interval. Okay. Okay. I hope that's clear. And page 34 to page 39, all of these equations are just trying to get to trying to calculate the distribution of beta 1 hat. Okay, it's optional. Okay, no one really needs to get through it. Okay. All right. So the larger the variance of x, the smaller the variance of beta 1. This one is not required. Okay, but its intuition is very direct. So if you have a lot of variation in x, there is more information in the data that you can use to fit the regression line. So this is more easily seen in a figure. Okay. Imagine you only have the blue, you imagine you only have the blue dots. Okay, how do you fit the data? Okay, imagine you only have the blue dot, then you probably cannot fit the data very well, right? Because it doesn't look like anything. Okay, now if you have all the dots, then it's easier for you to fit a line. Okay, so so the bigger the variance of x, the better. And if you have more dots, it's also better, right? Um, so let's say if you only have 3 observations, okay, then your line probably doesn't look too well. Okay, so the more observation, the better, and the more variance of the x, okay, the more variance in the x-axis is the better. Okay, all right. A summary of the sampling distribution of beta 1. Okay, so there are 3 assumptions we need, just like central limit theorem. We need 3 assumptions. The first one is, let's see, where's the first one? Oh, it disappeared. Okay, never mind. So we need 3 assumptions, and if 3 assumptions hold, then beta 1's distribution looks like normal. Okay, it is firstly unbiased. Second, variance of beta 1 hat equals to this thing, but you are not required to remember this equation, okay? Because standard error will be given in all of your future questions. Okay. because beta 1 hat goes to beta 1 once n goes to infinite, so beta 1 hat is also consistent, okay? When n is large, this thing is a standard normal distribution, okay? It's also called central limit theorem, okay? So you can also use central limit theorem to get to this. It is parallel to the sampling distribution of y bar. So far you have an idea that why I say that learning statistics is so important, because if you forget about everything in your statistic class, then you probably don't really understand what I'm talking about right here. Okay. All right. This is more calculation. This part is not required. Lastly, I'm gonna just go through a little bit of the least square assumptions for prediction. So predictions require good out of sample performance. And here if you want to predict, you don't want to predict out of your sample. So for example, let's say let's go back to this one. So the sample range is about 14 to 26, right? So this is 14. This is 14. This is about 26. So it's good for you to predict test scores of a class size that is between 14 to 26. Now let's say I have a class that has 30 students per teacher. Okay, and then you predict that this class is gonna have about how much? 630 test scores. Is this correct? So the answer of that is no. Why? Because this star point is out of your sample. Okay, if you want to predict something out of your sample and you don't have any information over there, then it probably doesn't make sense. Okay, so prediction only works within the sample range. Okay, if you have sample information between 14 to 26 students per teacher, then you can make good predictions within this range. If I asked you to predict the test score for a class of 30 students, then these predictions should not work well, okay? Simply because you don't have information over there, okay? All right, so that's it for chapter 4. I will see you next Tuesday for the exercise here, okay?